Stop breathing. Stop moving. Imagine you could freeze every molecule in your body, every photon in the room, and every vibration in the floor beneath you. You are seeking a state of absolute crystalline stillness. You want to reach a point where nothing is happening. You cannot dot in your everyday world. Zero is a destination. If you have $10 and I take $10, you have zero. It is a clean, logical conclusion. But in the subatomic realm, nature abhors a zero even more than it abhors a vacuum. To understand why particles appear to materialize from the void, you must first accept a disturbing truth. The universe is legally forbidden from being still. This isn't a limitation of our technology. It isn't because our microscopes aren't steady enough or our laboratories aren't quiet enough. It is a fundamental tax levied by the Heisenberg Uncertainty Principle. You likely know the popular version of this principle. You can't know a particle's position and its momentum at the same time. It's often taught as a blurry problem, as if the particle is a shy actor avoiding the spotlight. This is a comforting lie. The reality is more aggressive. The uncertainty principle applies to energy and time. There is a mathematical seesaw between these two variables. The more precisely you try to define a moment in time, the shorter the interval you look at, the more the energy in that space begins to wildly fluctuate. If you look at a billionth of a second, the energy doesn't just jitter. It screams. It swings from massive surpluses to massive deficits. Think of it as a cosmic bank account. On a human timescale, seconds, years, centuries, the universe is a strict accountant. Energy is conserved. It cannot be created or destroyed. The books must balance. But the universe allows for short-term embezzlement. If a particle wants to exist, it needs energy. Usually, it doesn't have enough. But because of the energy-time uncertainty, a particle can borrow a massive amount of energy from the vacuum, provided it pays it back almost instantly. The more energy it borrows, the faster it must return it. The heavy particle can only exist for a vanishingly small flash of time. A lighter one might linger a fraction longer. This means that what you call empty space is actually a high-frequency stock market of existence. At any given femtosecond, in every cubic centimeter of your brain, trillions of virtual particles are popping into being, looking around, and crashing back into non-existence. They are ghosts that haven't been caught yet. You think you are sitting in a silent room. You aren't. You are sitting in a storm of temporary realities that are failing to stay. Real only because they haven't found a way to hide their debt from the laws of physics. We used to think the vacuum was the stage upon which the play of the universe was performed. We were wrong. The vacuum is the play. The particles you see, the electrons in your screen, the protons in your atoms, are just a few actors who manage to stay on stage long enough for you to notice them. Everything else is just the noise of a universe that is physically incapable of doing nothing. If you open a physics textbook, you will see them. Elegant, spindly little drawings of lines meeting at vertices. An electron enters from the left. A photon zigzags away. Another electron exits to the right. You look at these, and you think you are seeing a snapshot. You think you are looking at a microscopic CCTV frame of a collision, a literal path taken by a literal thing. This is your first mistake. Richard Feynman did not invent these diagrams to show you what a particle is doing. He invented them to help us calculate the horrifying reality of what a particle could be doing. In the classical world, if you throw a ball from point A to point B, it follows a single predictable arc. In the quantum world, the particle takes every possible path simultaneously. It goes straight. It loops around the moon. It travels to the beginning of time and back. Feynman's path integral formulation tells us that to find the truth, We have to sum up the probabilities of every one of these infinite, absurd roots. Now, look closer at one of those diagrams. Notice the loops between the moment an electron starts its journey and the moment it ends. It doesn't just travel. It fluctuates. It might emit a virtual photon. That photon might then split into a virtual electron and a virtual positron. Those two might dance around each other for a billionth of a second before slamming back together, turning back into a photon, which is then reabsorbed by the original electron. These are the virtual transactions. They are the accounting ledgers of the vacuum. The disturbing part of Feynman's answer isn't that these things can happen. It's that they must happen for the math to work. If you try to calculate the behavior of a simple electron without accounting for these ghosts popping in and out of existence, your answer will be wrong. Every single time. This forces us to re-evaluate what a particle actually is. You imagine a little hard sphere, like a marble. But a marble has a defined edge. A marble doesn't borrow parts of itself from the void. Feynman's diagram suggests that a real particle is nothing more than a localized disturbance in a field that is constantly trying to create everything at once. It is a sum over histories. What you perceive as a solid object is actually a vibrating average of an infinite number of virtual events. You are not made of stuff. You are made of the mathematical remainder of a trillion fleeting appearances. The nowhere from which these particles appear is not a place. It is the field itself, a mathematical ocean that is always on, always trying to manifest, always pushing against the boundary of existence. We are simply the ripples that were loud enough to be heard above the static, if you follow Feynman's logic to its natural conclusion. You arrive at a nightmare. If every point in space is a boiling cauldron of virtual particles, if the vacuum is constantly birthing and killing electrons, quarks, and photons, then we have a bookkeeping problem. Every one of those fleeting particles carries a tiny non-zero amount of energy. And because there are an infinite number of points in space, and an infinite number of ways these virtual particles can loop and dance, the total energy of nothing should be infinite. This is the catastrophe. According to the math that describes our most successful theories, the energy contained in a single light bulb-sized volume of empty space should be enough to boil all the oceans on Earth. It should be enough to curve space-time so violently that the entire universe would have collapsed into a singularity the size of an atom billions of years ago. Clearly, this hasn't happened. You are still breathing. The universe is still expanding. Physicists found themselves in a state of intellectual panic. The math was perfect, but the result was impossible. They had discovered that nothing was infinitely heavy. To fix this, Feynman and his contemporaries had to perform a piece of mathematical surgery so controversial that even Feynman himself called it a shell game. It is called renormalization. Imagine you are trying to weigh a person, but they are standing in a hurricane. You can't get a clean reading because the wind is pushing down on the scale with massive, shifting force. To find the real weight, you decide to subtract the infinite force of the wind from your final measurement. In physics, we do the same. We take the infinite energy of the vacuum and we simply subtract it. We define the 0 point not as true zero, that is the level of the hurricane. We ignore the infinite roar of the vacuum because if we didn't, we couldn't do physics at all. This should disturb you. It means that our understanding of reality is built on a foundation of ignoring the infinities. We have decided, by fiat, that the screening chaos of the vacuum doesn't count toward the total. But Feynman knew this was a bandage, not a cure. It suggests that our real world, the one with solid chairs and predictable gravity, is just a thin, fragile crust floating on top of an infinite energetic abyss. We only exist because the infinities of the vacuum happen to cancel each other out almost perfectly, leaving behind a tiny manageable residue that we call matter. We are the leftovers of a cosmic cancellation. We are the rounding error in an equation that should have blown up the universe. You think the vacuum is empty because it looks quiet. But it only looks quiet because you are part of the noise that has been normalized away. Up to this point, you might be tempted to dismiss this as mathematical ghost hunting. You might think that virtual particles are just a clever bookkeeping trick, a way for physicists to make their equations balance without admitting they don't know what's actually happening. You want to believe that if you cannot see them, and they only exist for a billionth of a second, they aren't real. In 1948, Hendrik Casimir proved that nothing can move mountains. Or, at least, it can move metal. Imagine two perfectly flat, uncharged metal plates. You place them in a vacuum, a fraction of a hair's width apart. There is no static electricity. There is no gravity pulling them together. There is no air to push them. By every classical law of physics, they should sit there, motionless, forever. They don't. They are slammed together by an invisible, relentless pressure. To understand why, you have to stop thinking of the vacuum as an empty space and start thinking of it as a sea of waves. Every virtual particle is also a wave. In the vast, open space outside the plates, waves of every possible size, every possible wavelength can pop into existence. But in the tiny gap between the plates, only the small waves can fit. The long, powerful waves are physically excluded. They are too big for the room. This creates a lethal imbalance. There is more nothing on the outside than there is on the inside. The infinite variety of the vacuum outside the plates pushes harder than the restricted vacuum inside. This is the Casimir effect. It is the physical manifestation of the fact that the vacuum is not a zero. It is a pressurized environment. It is the proof that the accounting errors Feynman described have real, kinetic consequences. If you were small enough, you would feel it. You would feel the vacuum throb. You would feel the nothing around you constantly trying to crush you, not because of air pressure, but because of the sheer density of potential existence. The vacuum is not a lack of things. It is a presence of things that haven't quite happened yet. And when you restrict that presence, when you try to box in the void, it pushes back. It is the most honest moment in physics. The moment when we realize that the stage itself is trying to tear down the scenery. You think of an electron as a thing, a fundamental, indivisible point of matter. You imagine it as a tiny solid sphere with a negative charge, orbiting a nucleus like a planet. This is the comfort of the Bohr model, a map that is easy to read, but entirely fictitious. The reality is that you have never seen an electron. No one has. What we see, and what we measure in our most precise experiments, is a dressed particle. In 1947, a physicist named Willis Lamb noticed a tiny, inexplicable hiccup in the energy levels of a hydrogen atom. According to the best equations of the time, two specific states of the electron should have had the exact same energy. They were supposed to be identical twins. But Lamb found a minuscule shift. This Lamb shift was the smoking gun that proved the vacuum isn't just a background. It is an active participant in the identity of matter. To understand why, you have to accept that an electron is never alone. Because of the boiling sea of the vacuum we discussed, an electron is constantly interacting with the virtual particles popping up around it. More disturbingly, it is constantly interacting with itself. Imagine an electron moving through space. At any moment, it can emit a virtual photon. A split second later, it reabsorbs that same photon. It is as if the electron is constantly throwing a ball into the air and catching it. But while that ball, that virtual photon, is in flight, It can itself split into a virtual electron and a virtual positron. This means that what you call a single electron is actually a central core surrounded by a buzzing, chaotic cloud of virtual ghosts. Physicists call a hypothetical, isolated version of the particle the bare electron. But the bare electron is a fiction. It doesn't exist in our universe. If you could somehow strip away the cloud of virtual particles, the bare charge and bare mass of the electron would be infinite. It is only the interference of the vacuum, the way the virtual particles shield and dress the core, that gives us the finite, stable electron we see in our instrument's dot. This destroys the very concept of an individual object. If an electron's mass and charge are determined by its constant interaction with the nothingness around it, then where does the vacuum end and the particle begin? There is no clear boundary. You are not a collection of solid points. You are a collection of dressed excitations, blurred clouds of self-interaction that only appear solid because the vacuum is constantly pushing back against them. You think you are made of atoms, but an atom is mostly empty space, and that empty space is actually the very thing that defines the particles within it. Without the constant, ghostly interference of the void, the particles that make you would literally blow up to infinite size. You do not exist in spite of the vacuum. You exist as a localized symptom of it. Everything we have discussed there so far relies on a loophole. The universe is a lenient creditor. As long as a virtual particle pair annihilates, returning its borrowed energy to the vacuum within the time frame dictated by the uncertainty principle, the books remain balanced. The crime of existence is erased before it can be registered. But what happens if you interfere with the repayment? What happens if you separate the pair so they can never meet again? This is the nightmare of the event horizon dot. Imagine a virtual particle and its antiparticle twin popping into existence at the very edge of a black hole. Under normal circumstances, they would collide and vanish in a fraction of a nanosecond. But here, the geometry of space is warped beyond recognition. Before they can reunite, one particle is pulled across the threshold, the point of no return, while the other is flung outward into the cosmos dot. The pair has been forcibly divorced. They can no longer annihilate. The particle that escaped into the universe is now, for all intents and purposes, real. It has mass. It has momentum. It can hit a detector. It has been promoted from a virtual ghost to a permanent resident of reality. But there is a price. Energy cannot be created from nothing. If a real particle has appeared in the universe, the energy to create it must have come from somewhere. Since the vacuum cannot carry a permanent debt, the black hole is forced to pay the bill. The black hole loses a tiny fraction of its mass to compensate for the particle it stole from the void. This is Hawking. Radiation dot. It is the ultimate proof that the boundary between nothing and something is fragile. It suggests that real matter is just virtual matter that got lucky. If you stand near a black hole, you are watching the vacuum being ripped apart. Its internal fluctuations forced into the light of day. It reveals a terrifying symmetry. If a black hole can shrink by turning nothing into something, then the solid matter of the universe is not the primary state of being. It is merely the result of a cosmic separation. We are the particles that didn't fall back in. Everything we have discussed, the virtual particles, the shifting energy levels, the dressed mass of your own body, relies on one silent assumption. We assume that the vacuum we live in is the ground floor. We assume that this boiling sea of energy has reached its lowest possible state. But what if we are wrong? In physics, there is the concept of a metastable state. Think of a ball sitting in a slight dip halfway up a mountain. It is stable for now. It isn't moving, but it is not at the bottom. If you give it a tiny nudge, it will roll down to the true valley, releasing a massive amount of potential energy as it falls. Current measurements of the Higgs boson suggest that our vacuum, the very fabric of our reality, might be that ball on the shelf. We may be living in a false vacuum. If this is true, the nothing that created you is not finished. Somewhere in the cosmos, a quantum fluctuation could trigger a phase transition. A bubble of true vacuum could form a region where the laws of physics are fundamentally different, where the energy of the void is lower, and where the particles that make up your atoms simply cannot exist. This bubble would expand at the speed of light. You would never see it coming. There would be no sound, no flash, no warning. The nothing would simply redefine itself, and in an instant, the chemistry of your cells, the fusion in the sun, and the structure of gravity would be overwritten. The universe wouldn't end in a traditional sense. It would just stop being the version of reality that includes you. Richard Feynman's work showed us that the vacuum is the source of everything. But the philosophical awe lies in realizing that the vacuum is also the ultimate arbiter. We are the ripples on a surface that hasn't finished sinking. We are the brief, beautiful music played on a string that is still being tightened. You started this journey thinking that nothing was a void. You now know it is a pressurized, energetic, and potentially unstable foundation. You are a temporary loan from a bank that can change its interest rates at any moment. We do not live in a world of objects. We live in a moment of stolen time, held together by the restless, screaming silence of a vacuum that is still deciding what it wants to be.